There is not a single thing in the universe that stands still. Not one. You're spinning right now at over 1,000 miles per hour as Earth rotates beneath your feet, and you're orbiting the sun at 67,000 miles per hour, and the sun itself is racing through the galaxy at 500,000 miles per hour, and the galaxy is spinning through space at over 1,000,000 miles per hour, and yet you feel none of it. You're sitting perfectly still, listening to this, unaware that you're participating in a cosmic dance that has never, not once in 13.8 billion years, stopped moving. Every star spins, every planet spins, every galaxy spins. Even the smallest particles of matter spin in ways that defy everything we thought we understood about reality. And here's the part that should keep you awake at night, except it won't. Because this is the kind of mystery that lulls you into wonder. No one truly knows why. We can describe it, measure it, predict it, but the deepest question remains unanswered. Why is everything spinning at all? Welcome. I'm glad you're here. This is a space where curiosity becomes a companion to rest, where the profound mysteries of existence unfold gently, like waves lapping at the shore of consciousness. If you're new to this channel, we explore the universe's most fascinating truths in a calm, meditative way, knowledge that invites wonder without demanding wakefulness. If you'd like more journeys like this one, I'd be grateful if you'd subscribe and turn on notifications. It helps these explorations continue, and it means you'll have a library of calm curiosity waiting whenever you need it. Tonight, we're going to explore something so fundamental, so universal, that it's hiding in plain sight. We're going to understand why everything, absolutely everything, is spinning. And as we move through this together, you'll discover that this single question opens doors to nearly every mystery in physics, from the birth of galaxies to the strange quantum world inside atoms, from the reason you exist at all to the ultimate fate of everything. Let's begin with something you can feel, even though you don't feel it. You are standing on a sphere that's spinning at over 1,000 miles per hour. Right now. As you listen to these words, you're moving faster than the speed of sound, rotating with a planet that completes one full turn every 24 hours. At the equator, the surface of Earth moves at 1,037 miles per hour. That's faster than a commercial jet. And yet you feel absolutely nothing. No wind against your face, no sense of motion, no indication whatsoever that you're hurtling through space at incomprehensible speed. The reason you don't feel it is because everything around you, the air, the ground, the buildings, the trees, is moving with you at exactly the same speed. You're all spinning together, locked in this rotation, and your body has no reference point to tell you you're moving at all. But Earth's spin isn't something that just happens to be convenient for day and night. It's a remnant of the planet's birth. 4.5 billion years ago, Earth formed from a disk of dust and gas swirling around the young sun. That disk was already spinning, and when particles collided and clumped together to form our planet, they brought that spin with them. Earth inherited its rotation from the cosmic cloud that created it, and here's what makes this profound. That spin has been slowing down gradually for billions of years. Every day is getting longer, microscopically longer, but longer nonetheless. The moon's gravitational pull creates tides, and those tides create friction. And that friction acts like a brake on Earth's rotation. A day today is longer than a day was when dinosaurs walked the Earth. Back then, a day was only about 23 hours long. Go back far enough to when Earth first formed, and a day might have lasted only 6 hours, which means that time itself, in a way, is stretching. The moon is pulling on Earth's oceans, and in doing so, it's stealing some of Earth's rotational energy. And where does that energy go? It goes into the moon's orbit. The moon is slowly spiraling away from Earth, moving about 1.5 inches farther every single year. Billions of years from now, the moon will be so distant that it will no longer create the strong tides that have shaped life on this planet. Days will be much longer. The night sky will be different. And all of this traces back to one simple fact. Everything spins, and that spin connects to everything else. But let's go deeper, because Earth's spin is just the beginning. The sun spins too. It takes about 25 days for the sun to complete one rotation at its equator. Though the sun doesn't spin like a solid object, different parts rotate at different speeds, faster at the equator and slower near the poles. This is because the sun is made of plasma, a kind of superheated gas, and there's no solid surface to keep it rotating uniformly. The sun's spin creates its magnetic field, and that magnetic field drives solar flares, coronal mass ejections, and the beautiful auroras that dance across Earth's polar skies. Without the sun's spin, there would be no magnetic field. Without the magnetic field, there would be no protection from cosmic radiation. The sun's rotation is part of what makes life on Earth possible. And the sun isn't standing still in space either. It's orbiting the center of the Milky Way galaxy at roughly 514,000 miles per hour, completing one full orbit every 230 million years. The last time the sun was in its current position in the galaxy, dinosaurs hadn't even appeared yet. One complete orbit of the galaxy is called a cosmic year, and Earth has only experienced about 20 cosmic years since it formed. 20 trips around the galaxy, that's all. In the grand scale of cosmic time, we're still in the early chapters of our journey, and the Milky Way itself? It's spinning too. The entire galaxy rotates, all 200 billion stars swirling around a supermassive black hole at the center. Our solar system is moving through the galaxy at over 500,000 miles per hour, but it still takes 230 million years to complete one orbit because the galaxy is so incomprehensibly vast. And here's something that should give you pause. The stars near the edge of the galaxy are moving just as fast as stars closer to the center, which shouldn't be possible according to the laws of gravity. There isn't enough visible matter in the galaxy to explain why those outer stars aren't flying off into space. This is one of the reasons scientists believe in dark matter, some invisible substance that holds galaxies together, allowing them to spin faster than they should. We can't see it, we can't touch it, but we know it's there because without it, galaxies would tear themselves apart. So now we have this picture. You, standing on a spinning Earth, orbiting a spinning sun, which is orbiting the center of a spinning galaxy, which itself is moving through space in a cluster of galaxies, all of them spinning, all of them in motion, and none of them ever stopping. But why? Why is everything spinning in the first place? The answer begins at the very start of the universe. In the first moments after the Big Bang, the universe was a hot, dense soup of energy and particles, expanding rapidly in all directions. But that expansion wasn't perfectly uniform. There were tiny fluctuations, small differences in density from one region to another. As the universe expanded and cooled, gravity began to pull matter together into clumps. And here's the critical part. Even the smallest amount of rotation in those early clumps got amplified as they collapsed. This is because of something called conservation of angular momentum, the same principle that makes an ice skater spin faster when they pull their arms in. As clouds of gas collapsed under gravity to form stars and galaxies, they spun faster and faster, converting gravitational energy into rotational energy. And once something starts spinning, it doesn't stop. There's no friction in space to slow things down, no air resistance, no surface to drag against. Spin is conserved. A spinning object will keep spinning forever unless something acts on it to transfer that spin elsewhere. This is why galaxies spin. This is why stars spin. This is why planets spin. They all inherited their rotation from the clouds of gas and dust that collapsed to form them, and that rotation came from tiny fluctuations in the early universe, amplified over billions of years by gravity. But there's something even stranger happening at the smallest scales of reality. Inside atoms, electrons don't orbit the nucleus the way planets orbit the sun. That's an outdated model. Instead, electrons exist in probability clouds, regions where they're likely to be found, and they have a property called spin. Now, here's where language fails us a bit, because electrons aren't actually spinning like little tops. The word spin is just the best term physicists could come up with to describe a quantum property that has no direct analogy in the everyday world. Electron spin is a fundamental property of matter, like mass or charge, and it comes in two varieties, spin up and spin down. And this quantum spin is what makes chemistry possible. It's what determines how atoms bond together to form molecules. It's the reason you exist. The Pauli exclusion principle states that no two electrons in an atom can have the same quantum state, which means they can't have the same spin. This forces electrons into different energy levels, creating the structure of atoms, the periodic table, and all of chemistry. Without quantum spin, matter as we know it couldn't exist. But quantum spin gets even stranger. When you measure the spin of an electron, you always get one of two results: spin up or spin down. Never anything in between. The electron doesn't have a definite spin until you measure it. It exists in a superposition of both states simultaneously. And the moment you measure it, the superposition collapses, and the electron chooses one state. This is one of the fundamental mysteries of quantum mechanics, and it's connected to spin. The universe, at its deepest level, seems to be made of things that are spinning in ways we can't fully visualize or understand. And it's not just electrons. Protons spin, neutrons spin, quarks, the particles that make up protons and neutrons, have spin too. Everything at the quantum level has this intrinsic property of spin, and no one knows why. It's built into the fabric of reality. It's not something particles do. It's something they are. Consider for a moment what this means. You're made of atoms, and those atoms are made of particles that have this bizarre quantum property called spin. Every cell in your body, every molecule, every atom is part of this spinning universe, from the quantum level all the way up to galaxies. Spin is woven into existence itself. And there's more. Black holes spin too. When a massive star collapses at the end of its life, it doesn't just become a point of infinite density. it becomes a spinning point of infinite density. The rotation of the original star is conserved, concentrated into an impossibly small space, and the black hole spins at tremendous speeds. Some black holes spin so fast that they drag space-time itself along with them, creating a region called the ergosphere where nothing can stand still. Even light gets dragged around the black hole in the direction of its spin. This is called frame dragging, and it's one of the strangest predictions of Einstein's theory of general relativity. Space-time itself can be twisted by rotation, and here's the astonishing part. We've measured this. We've detected frame dragging around Earth. Our planet's rotation is dragging space-time along with it, creating a tiny twist in the fabric of reality around us. The effect is minuscule. Earth isn't massive or dense enough to create a significant twist, but it's there, measurable, real. You're not just spinning through space, you're spinning space-time itself, which brings us to pulsars. These are neutron stars, the collapsed cores of massive stars that spin at extraordinary speeds. Some pulsars rotate hundreds of times per second. Imagine a star more massive than the sun, compressed into a sphere only about 12 miles across, spinning faster than a blender blade. These objects emit beams of radiation from their magnetic poles, and as they spin, those beams sweep across space like lighthouse beams. When one of those beams points toward Earth, we detect a pulse. Hence, pulsar. The fastest pulsar we've discovered spins 716 times per second. That's 716 complete rotations every single second. At its equator, the surface is moving at roughly 24% the speed of light, and it's not slowing down in any way we can notice. Pulsars are so dense and have so little friction that they can maintain their rotation for millions of years. They're the most accurate clocks in the universe, more regular than any timepiece humans have ever built. And all of this, from galaxies to black holes to pulsars to atoms, is connected by the same principle: angular momentum. Spin is a form of momentum, and momentum is conserved. Once something is spinning, it will keep spinning unless something else interferes. This is why the universe is full of spinning objects. They inherited their spin from earlier spinning objects, which inherited it from earlier ones still, all the way back to the first tiny fluctuations in the early universe. But here's a question that might seem simple, but isn't. Why did the early universe have any rotation at all? Why wasn't it perfectly symmetric, expanding uniformly in all directions with no spin? And the truth is, we don't fully know. There are theories. Quantum fluctuations in the first fraction of a second after the Big Bang might have seeded tiny rotations. Or perhaps the universe itself has some net rotation, though that seems unlikely given what we observe. The honest answer is that the origin of cosmic spin is still one of the open questions in cosmology. What we do know is that spin is deeply connected to symmetry. In physics, every symmetry corresponds to a conservation law. The fact that the laws of physics are the same at every point in space means that momentum is conserved. The fact that the laws of physics are the same at every moment in time means that energy is conserved. And the fact that the laws of physics don't depend on which direction you're facing means that angular momentum, spin, is conserved. Spin is fundamental because symmetry is fundamental. The universe has rotational symmetry, and that symmetry locks spin into place. Once something starts spinning, the universe's laws guarantee it will keep spinning. And this connects to something beautiful. The reason planets orbit stars, the reason moons orbit planets, the reason galaxies hold together, all of it traces back to spin and gravity working together. When a cloud of gas collapses to form a star, it's spinning, and that spin flattens the cloud into a disk. Planets form from that disk, and they inherit the disk's rotation, which is why all the planets in our solar system orbit the sun in roughly the same plane and in the same direction. They're all part of the same spinning system, born from the same rotating cloud. And moons form the same way, from disks of debris orbiting planets. Our moon is an exception. It formed from a massive collision between early Earth and a Mars-sized object, an impact so violent it threw debris into orbit, and that debris eventually coalesced into the moon. But even in this catastrophic event, spin played a role. The collision gave Earth much of its rotational energy, and the debris disk that formed the moon was spinning too. There's something almost poetic about this. Everything in the universe is connected by spin. You're made of atoms that spin. You're standing on a planet that spins. That planet orbits a star that spins. The star orbits a galaxy that spins. And all of this motion, all of this endless rotation, is part of a cosmic symphony that's been playing for 13.8 billion years. And it's never going to stop. The universe will keep expanding. Galaxies will keep spinning. Stars will keep rotating. Planets will keep orbiting. Even as the universe grows colder and emptier, even as stars burn out and galaxies drift apart, the spin will remain. It's one of the few things that's truly eternal. As you drift towards sleep tonight, consider this. You're part of that eternal motion. You're spinning with the Earth, orbiting with the sun, moving through the galaxy, participating in a cosmic dance that connects you to everything that has ever existed and everything that ever will. You're not separate from the universe. You're part of its spin, part of its motion, part of its endless, beautiful rotation through space and time. The spin of the universe isn't just motion, it's memory. Every rotating object carries within it the history of how it came to be, encoded in the speed and direction of its rotation. When you look at a spinning galaxy, you're seeing the fossil record of its formation, the accumulated spin of billions of years of collisions, mergers, and gravitational interactions. Nothing in the cosmos spins by accident. Every rotation tells a story, and some of those stories are violent beyond imagination. When two galaxies collide, and yes, galaxies do collide, despite the vast emptiness of space, their spins determine what happens next. If they're rotating in the same direction, they might merge smoothly, their stars and gas mingling over hundreds of millions of years to form a larger galaxy. If they're rotating in opposite directions, the collision becomes chaotic, stars flung in all directions, gas clouds compressed until they burst into furious waves of star formation. Our own Milky Way is on a collision course with the Andromeda Galaxy. In about 4 billion years, they'll meet, and their spins will determine the shape of the new galaxy that emerges from that cosmic encounter. But here's what's remarkable. Even in a galaxy collision, individual stars almost never actually hit each other. Galaxies are so vast and stars are so small relative to the distances between them that two galaxies can pass right through each other with their stars threading between each other like dancers in a crowded ballroom. It's the gravitational interactions, the tidal forces, the disruption of spin that does the real damage. The structure changes, the rotation changes, but the stars themselves, for the most part, sail past each other untouched. This tells us something profound about the nature of rotation in the universe. Spin operates at scales that dwarf the objects themselves. A galaxy's spin isn't really about individual stars. It's about the overall distribution of mass, the way gravity organizes everything into rotating systems. And this pattern repeats at every scale. Solar systems spin as unified systems. Planets spin within those systems. Weather patterns spin on those planets. Hurricanes are spinning systems within spinning systems within spinning systems. And at the center of a hurricane is an eye, a region of calm where the spin temporarily releases its grip. And that eye, that calm center, exists because of something called the Coriolis effect, which is itself a consequence of Earth's rotation. As Earth spins, anything moving across its surface appears to curve. In the northern hemisphere, moving objects curve to the right. In the southern hemisphere, they curve to the left. This isn't because some force is pushing them sideways. It's because they're moving across a rotating sphere, and from our perspective on that sphere, their straight-line motion looks curved. The Coriolis effect is why hurricanes spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. It's why ocean currents curve. It's why artillery shells fired over long distances have to account for Earth's rotation, or they'll miss their targets. The universe is full of these nested spins, wheels within wheels, each one influencing the others in ways both subtle and profound. And at the very smallest scale, inside the nucleus of every atom, there's another kind of spin happening that's even stranger than anything we've discussed so far. Atomic nuclei spin too. Just like electrons, protons, and neutrons have quantum spin, and when they combine to form a nucleus, their spins can add up or cancel out depending on how they're arranged. Some nuclei have a net spin, others don't. And this nuclear spin is what makes MRI machines possible. Magnetic resonance imaging. When you place atomic nuclei in a strong magnetic field, their spins align with the field. And then if you hit them with radio waves at just the right frequency, you can flip their spins. When the spins flip back, they emit radio waves that can be detected, and those signals can be used to create incredibly detailed images of the inside of your body. The entire medical technology of MRI exists because atomic nuclei spin. But nuclear spin has another consequence, one that's more unsettling. Some atomic nuclei are unstable. Their spin configurations don't quite balance out, and over time, they decay, releasing radiation as they transform into more stable forms. This is radioactivity. Uranium decays into lead, carbon-14 decays into nitrogen. Potassium-40, which exists in every banana you eat, slowly decays inside the fruit, making bananas technically radioactive. Not dangerous, just measurably radioactive. And it's all because of the quantum spin of particles inside atomic nuclei. This connects to something most people never think about. There are radioactive atoms inside your body right now. Potassium-40 in your muscles, carbon-14 in every cell, tiny amounts of uranium and thorium in your bones. These atoms are decaying one by one, emitting radiation as their nuclei rearrange themselves into more stable configurations. You're slightly radioactive. Every human is. And this has been true for all of human history. We evolved in a world where background radiation was simply part of existence, and our cells developed mechanisms to repair the damage it causes. And all of this traces back to spin. The stability of atomic nuclei depends on the arrangement of quantum spins. The behavior of electrons depends on their spin states. The structure of matter itself is shaped by spin at the quantum level. And yet, if you ask a physicist what spin really is, what it means for a particle to have spin when it's not actually rotating, they'll tell you honestly that no one fully understands it. Spin is a mathematical property, a feature of quantum field theory, but it doesn't have a simple physical interpretation the way classical rotation does. Which brings us to one of the deepest mysteries in physics. Why does the universe have the properties it has? Why do particles have spin? Why is angular momentum conserved? Why does space-time itself respond to rotation? These aren't questions with easy answers. They're not even questions with hard answers. They're questions that push us to the very edge of what physics can explain. Some physicists believe that spin might be connected to the geometry of space-time at scales far smaller than we can probe. Others think it might be an emergent property of some deeper, more fundamental theory we haven't discovered yet. String theory, for example, suggests that particles aren't point-like objects but tiny vibrating strings, and their spin might be related to the way they vibrate. But string theory is still speculative, still unproven, and the true nature of quantum spin remains one of the unsolved problems of modern physics. And yet, despite this deep uncertainty, we can use spin to build technology. We can manipulate electron spins to create quantum computers. We can use nuclear spin to image the inside of living bodies. We can measure the spin of pulsars to test general relativity. We don't need to fully understand what spin is to use it, to harness it, to build entire fields of science and engineering on top of it. This is one of the strange paradoxes of physics. We know how things work without always knowing why they work that way. We can predict, with extraordinary precision, what will happen when particles interact, how spins will behave, how angular momentum will be conserved. But the deeper question, why the universe is structured this way in the first place, remains tantalizingly out of reach. Consider the spin of Venus. Every planet in our solar system rotates in the same direction. They all spin counterclockwise when viewed from above the sun's north pole. Every planet except Venus. Venus spins clockwise, in the opposite direction from all the others, and it spins incredibly slowly, taking 243 Earth days to complete one rotation. That's longer than Venus's year, which is only 225 Earth days. On Venus, a day is longer than a year, and no one knows exactly why Venus spins backward. The most likely explanation is that Venus was hit by a massive object early in its history, an impact so large it reversed the planet's rotation. Or perhaps gravitational interactions with the sun gradually flipped Venus's spin over billions of years. The truth is, we're not certain. What we are certain of is that Venus's strange rotation has consequences. Without a fast spin, Venus doesn't have a strong magnetic field. Earth's magnetic field is generated by the rotation of molten iron in its core, a spinning dynamo that creates the protective magnetic bubble around our planet. Venus's core might be molten too, but its slow rotation means no dynamo, no magnetic field. And without a magnetic field, Venus is exposed to the full force of the solar wind, the stream of charged particles flowing from the sun. Over billions of years, the solar wind has stripped away most of Venus's water, leaving the planet a dry, scorching hellscape with surface temperatures hot enough to melt lead. Spin, or the lack of it, determined Venus's fate. And then there's Uranus, which spins on its side. Most planets have their rotation axes nearly perpendicular to their orbital planes. They spin upright, more or less. Uranus's axis is tilted 98 degrees, which means it essentially rolls along its orbit like a barrel. For half of its 84 Earth-year orbit, the North Pole points toward the Sun, experiencing constant daylight for 42 years. Then, for the other half, the South Pole points toward the Sun, while the North Pole endures 42 years of darkness. This extreme tilt is almost certainly the result of a collision early in the solar system's history, another massive impact that knocked Uranus over and left it spinning on its side. These collisions, these cosmic accidents, shaped the rotation of the planets. And those rotations, in turn, shaped everything about those worlds, their magnetic fields, their climates, their potential for life. Spin isn't just motion, it's destiny. Back on Earth, there's a more subtle consequence of our planet's rotation that affects every living thing. Because Earth spins, day and night happen in a predictable rhythm, and life evolved to synchronize with that rhythm. Nearly every organism on Earth has an internal biological clock called a circadian rhythm, a roughly 24-hour cycle that regulates sleep, metabolism, and countless other biological processes. Your body knows when it's day and when it's night, not because you consciously track time, but because billions of years of evolution have wired that rhythm into your cells. And here's what's fascinating. Circadian rhythms persist even in the absence of external cues. If you put a person in a cave with no sunlight, no clocks, no way to tell time, their body will still follow a roughly 24-hour cycle. It won't be exactly 24 hours. For most people, it's slightly longer, about 24.5 hours. But it's close enough that it's clearly a response to Earth's rotation. Your body is synchronized with the spin of the planet. Plants have circadian rhythms too. They track the sun's movement across the sky, adjusting their leaves to maximize sunlight exposure. Sunflowers famously follow the sun during the day, rotating from east to west, and then reset at night, turning back east in preparation for sunrise. This behavior, called heliotropism, is driven by circadian clocks inside the plant's cells. The plant knows which way the sun should be at any given time, even if clouds obscure it, because its internal rhythm anticipates Earth's rotation. And bacteria have circadian rhythms. Cyanobacteria, some of the oldest living organisms on Earth, have molecular clocks that follow 24-hour cycles. These are single-celled organisms with no brain, no nervous system, no complex structures at all, and yet they track time with remarkable precision. The circadian rhythm is so fundamental to life on Earth that it exists in organisms that have been around for over 3 billion years. All of this because Earth spins. But there are places in the universe where spin becomes something truly alien. Neutron stars, which we touched on earlier, are so dense that a teaspoon of neutron star material would weigh about 1 billion tons. The gravity at the surface is so intense that if you dropped an object from a height of 1 meter, it would hit the ground at roughly 2,000 kilometers per second, about 0.7% the speed of light. And these objects spin. Some of them spin hundreds of times per second. Now imagine what that means for the structure of the star itself. At those rotation speeds, the neutron star bulges at the equator. It's no longer a perfect sphere. It's an oblate spheroid, wider at the middle than at the poles. And the faster it spins, the more pronounced the bulge becomes. If a neutron star spun any faster, if it rotated much more than about 1,000 times per second, it would tear itself apart. The centrifugal force at the equator would overcome even the intense gravity holding the star together, and material would start flying off into space. So there's a speed limit to spin. Not a law that says you can't spin that fast, but a practical limit where the structure can't hold together anymore. And this limit applies to everything. Planets can only spin so fast before they start shedding material from their equators. Stars can only spin so fast before their surfaces begin to tear away. Even black holes have a maximum spin rate. At the theoretical limit, the event horizon becomes so oblate that it would expose the singularity inside, though physicists don't think this actually happens in nature. Spin has limits, rotation has consequences, and those consequences shape the universe in ways both subtle and dramatic. There's another consequence of spin that's worth contemplating. When objects spin, they create what's called angular momentum, and angular momentum has a direction. If you're looking down at Earth from above the North Pole, the planet is spinning counterclockwise, and we say its angular momentum vector points upward, out of the North Pole. This direction matters. Angular momentum vectors can add together, cancel out, or interact in complex ways. When two spinning objects interact gravitationally, their angular momentum vectors influence how they move. This is why binary star systems can be so complicated. Two stars orbiting each other, each spinning on its own axis, each pulling on the other with gravity. Their spins can be aligned, or tilted, or completely opposite. And over time, tidal forces can synchronize their spins, locking them into configurations where they always show the same face to each other, just like the moon always shows the same face to Earth. The moon became tidally locked billions of years ago. Its rotation synchronized perfectly with its orbit so that one side perpetually faces Earth and the other side remains forever hidden. And this is happening to Earth too, very slowly. The same tidal forces that locked the moon's rotation are now working on Earth, gradually slowing our rotation and pulling us toward a future where Earth and moon are both tidally locked, always showing the same face to each other. But this process takes billions of years, and the sun will become a red giant long before it happens, so it's not something we'll ever witness. Still, it's happening. The moon is pulling on Earth, Earth is slowing down, and eventually, the dance will reach a kind of equilibrium. Except there's no true equilibrium in the universe. Everything is always changing, always evolving, always moving towards some new configuration. Even in a tidally locked system, other forces are at work. Other planets exert tiny gravitational tugs. The sun's mass loss as it burns fuel subtly changes orbital dynamics. Passing stars could disturb the system millions of years from now. Nothing is truly stable. Everything is always in motion, always spinning, always responding to forces we can barely perceive. And at the largest scales, even galaxy clusters spin. Groups of galaxies, bound together by gravity into vast cosmic structures hundreds of millions of light years across, have a collective rotation. It's incredibly slow, It might take billions of years for a galaxy cluster to complete even a fraction of a rotation, but it's there, measurable, real. The universe itself is spinning at every scale, from the smallest particles to the largest structures, and that spin connects everything in a web of angular momentum that spans all of space and time. As you rest now, think about this. You're not just on a spinning planet. You're inside a spinning solar system, inside a spinning galaxy, inside a rotating cluster of galaxies, inside a universe that may itself have some kind of net rotation we haven't detected yet. You're nested inside wheels within wheels, spins within spins, a cosmic architecture of motion that's so vast and so intricate that we've only just begun to map its full extent. And every breath you take, every heartbeat, every moment of consciousness, it's all happening while you spin through space at 1,000,000 miles per hour, part of a cosmic dance that will never end. The relationship between spin and time is more intimate than most people realize. When Einstein developed his theory of relativity, he discovered that time isn't absolute. It flows at different rates depending on how fast you're moving and how deep you are in a gravitational field. But there's another effect, one that's less famous but equally profound. Time flows differently depending on how fast something is spinning. If you could stand at the equator of a rapidly spinning neutron star, assuming you could somehow survive the impossible gravity, time would pass more slowly for you than for someone far away from the star. The spin itself warps space-time, creating a gradient in the flow of time from the star's poles to its equator. This isn't just theoretical. GPS satellites have to account for relativistic time dilation, including effects from Earth's rotation. The satellites are moving fast relative to the ground, and they're higher up in Earth's gravitational field, so time passes slightly faster for them than it does for you standing on the surface. But they're also affected by Earth's spin and their own orbital motion. All of these factors, gravity, velocity, rotation, combine to create tiny differences in how fast time flows. Without corrections for these relativistic effects, GPS would accumulate errors of several kilometers per day. Your phone knows where you are because engineers accounted for the way spin affects time. And this leads to something even stranger. Inside a rotating black hole, the structure of space-time becomes so twisted that the concepts of space and time start to trade places. Near the event horizon of a spinning black hole, there are regions where moving forward in time requires moving in the direction of the black hole's rotation. You can't stand still, even in principle. The spin of the black hole drags space-time along with it so severely that remaining stationary would require moving faster than light, which is impossible. So you're forced to move, swept along by the rotation of space-time itself, like a leaf caught in a whirlpool. And at the very center of a rotating black hole, the singularity, the point where density becomes infinite, isn't a point at all. It's a ring. The rotation prevents the collapse to a true point, instead forming a ring-shaped singularity that, according to the mathematics, might even be a gateway to other regions of space-time. These are called Kerr black holes, named after the physicist Roy Kerr, who first described their properties in 1963. Whether these ring singularities actually exist in nature is still debated. The mathematics allows for them, but nature might have other ideas. Still, the fact that rotation fundamentally changes the structure of a black hole tells us something profound. Spin isn't just motion through space. It's a property that reshapes reality itself. Let's return to something more familiar, but no less mysterious. Water swirling down a drain spins, and there's a common belief that water in the northern hemisphere always drains counterclockwise because of the Coriolis effect, while water in the southern hemisphere drains clockwise. This is mostly a myth. The Coriolis effect is real, but it's far too weak to influence something as small as a bathtub or sink. For water draining from a tub, the direction of spin is determined by the initial motion of the water, the shape of the drain, imperfections in the basin, factors that completely overwhelm the subtle influence of Earth's rotation. But scale that up, and the Coriolis effect becomes dominant. Large bodies of water, ocean currents for example, absolutely are influenced by Earth's spin. The Gulf Stream, which carries warm water from the Caribbean up along the eastern coast of North America, curves to the right as it flows northward, exactly as the Coriolis effect predicts. In the North Atlantic, ocean currents form a clockwise gyre. In the South Atlantic, they form a counterclockwise gyre. These patterns exist because of Earth's rotation, because the planet beneath the water is spinning, dragging the water along with it in ways that create these massive circular flows. And the atmosphere spins too, creating wind patterns that mirror the ocean's gyres. The trade winds near the equator blow from east to west. The westerlies in mid-latitudes blow from west to east. These patterns exist because air moves across a rotating sphere, and the Coriolis effect bends that motion into predictable paths. Without Earth's rotation, weather would be completely different. There would be no hurricanes, no jet streams, no consistent wind patterns. Air would simply flow from hot regions to cold regions in straight lines, and the climate of Earth would be unrecognizable. Pilots have to account for Earth's rotation when flying long distances. If you fly from New York to Los Angeles, you're traveling west, moving against Earth's rotation. The planet is turning eastward beneath you at about 800 miles per hour at that latitude. And though the atmosphere moves with the planet, the Coriolis effect still subtly influences your flight path. Autopilots compensate automatically, nudging the plane to counter the effect, but without those corrections, you drift off course. The spin of the planet affects every journey, whether we notice it or not. Even the shape of Earth itself is determined by spin. Earth isn't a perfect sphere. It's an oblate spheroid, slightly flattened at the poles and bulging at the equator. The equatorial diameter is about 27 miles greater than the polar diameter. This bulge exists because Earth is spinning. The centrifugal effect of rotation pushes material outward at the equator, and over millions of years, the planet's semi-molten interior has settled into a shape that balances gravity and rotation. If Earth stopped spinning, it would gradually become more spherical, the equatorial bulge slowly flowing back toward the poles over geological timescales. And this connects to something most people never consider. Mountains are, in a sense, fighting against Earth's rotation. Everest rises 29,000 feet above sea level, a massive pile of rock pushing upward against gravity. But gravity at the equator is slightly weaker than at the poles because you're farther from Earth's center due to the equatorial bulge, and because the centrifugal effect of rotation partially counteracts gravity's pull. If you weighed 200 pounds at the North Pole, you'd weigh about 199 pounds at the equator. The difference is small, but it's measurable. and it exists because Earth spins. This means that mountains at the equator are, in a tiny way, easier to climb than mountains at higher latitudes. Not because the climbing is physically easier, but because you weigh slightly less. Gravity's grip is just a bit weaker, and if you're standing on top of a mountain at the equator, you're moving through space faster than anyone else on the planet, faster than someone at sea level, faster than someone at the poles. You're at the outermost edge of Earth's rotation, whipping through space at over 1,000 miles per hour. Let's go deeper into the quantum realm, where spin becomes even more paradoxical. When two particles interact, they can become entangled, meaning their quantum states are linked in ways that transcend distance. If you measure the spin of one entangled particle and find its spin up, the other particle will instantly be spin down, no matter how far apart they are. Einstein famously called this spooky action at a distance because it seemed to violate the principle that information can't travel faster than light. But quantum entanglement doesn't actually transmit information. You can't use it to send messages faster than light because the measurement results are random. You can't control what result you'll get when you measure a particle's spin. What entanglement tells us is that quantum particles don't have definite properties until they're measured. Before measurement, an entangled pair exists in a superposition, both spin up and spin down simultaneously, and the act of measuring one particle instantaneously determines the state of both. This has been tested experimentally thousands of times, and the results are clear. Entanglement is real. Particles can be separated by kilometers, even potentially by light years, and they'll still exhibit this strange correlation. Their spins remain linked across space, not because they're sending signals to each other, but because they're part of a single quantum system that doesn't respect our intuitive notions of locality. And this quantum spin entanglement is being used to build quantum computers. These machines exploit the fact that quantum bits, qubits, can exist in superpositions of spin states, allowing them to perform certain calculations exponentially faster than classical computers. A qubit can be spin up, spin down, or both simultaneously, and by entangling multiple qubits, you can create states that represent vast numbers of possibilities all at once. When you run a calculation on a quantum computer, you're essentially exploring many different answers in parallel, and the quantum system naturally converges on the correct results. This technology is still in its infancy, but it's already demonstrating capabilities that classical computers can't match. Google's quantum computer recently solved a problem in 200 seconds that would take the world's fastest supercomputer 10,000 years. And all of this is possible because particles have spin, because spin can be entangled, because the quantum world operates according to rules that seem impossible from our everyday perspective. But let's return to the cosmos, where spin continues to shape reality in ways both beautiful and violent. When a massive star runs out of fuel and its core collapses, the resulting explosion, a supernova, is one of the most energetic events in the universe. For a few weeks, a single supernova can outshine an entire galaxy, releasing as much energy in that brief time as our sun will emit over its entire 10 billion year lifetime. And the energy doesn't radiate outward uniformly. Supernovae are asymmetric, their explosions shaped by the rotation of the collapsing core. If the core is spinning rapidly, the supernova tends to explode along the rotation axis, creating jets of material that blast out from the poles while the equator expands more slowly. This is why supernova remnants often have hourglass or bipolar shapes. The spin of the dying star carved its death into a specific geometry. And when the core collapses into a neutron star or black hole, it retains that spin, often rotating at incredible speeds because of conservation of angular momentum. Some of these remnants become pulsars, as we discussed earlier, but others become magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. These magnetic fields are generated by the combination of rapid rotation and the movement of charged particles in the neutron star's crust. A magnetar's magnetic field is so intense that it can strip electrons from atoms at distances of thousands of kilometers. If a magnetar existed where the moon orbits Earth, its magnetic field would be strong enough to disrupt the molecular bonds in your body from that distance. And occasionally, magnetars experience starquakes, sudden shifts in their crusts as the intense magnetic field twists and rearranges itself. When this happens, the magnetar releases a burst of gamma rays so powerful that it can be detected across the entire galaxy. In 2004, a magnetar called SGR 180620, located 50,000 light-years away, released a burst that hit Earth's atmosphere and ionized the upper layers, temporarily disrupting radio communications. This happened from an object the size of a small city, halfway across the galaxy, and the energy release in that fraction of a second was more than the sun emits in 250,000 years, all because of spin. The rotation created the magnetic field. The magnetic field stored enormous energy, and the starquake released that energy in an instant. There's a type of spinning system that exists much closer to home, one you might have experienced if you've ever been on a playground merry-go-round. When you're standing at the center of a spinning platform, it's relatively easy to stay balanced, but walk toward the outer edge, and suddenly you feel a force pulling you outward, trying to throw you off. This isn't a real force in the physics sense. It's a consequence of your body trying to move in a straight line while the platform rotates beneath you. From your perspective on the spinning platform, it feels like a force pushing you outward. We call it centrifugal force, though technically it's an inertial effect, not a true force. But here's what's interesting. From the perspective of someone standing still off the merry-go-round, there's no outward force at all. They just see you moving in a circle, held in place by friction or by gripping the rail. The centrifugal force only exists from your rotating frame of reference. It's what physicists call a fictitious force, something that appears when you're in an accelerating or rotating reference frame, but disappears when you look at the situation from a non-rotating perspective. And yet, fictitious or not, these forces have real effects. Engineers designing centrifuges for separating blood components or training astronauts have to account for centrifugal force. It doesn't matter that it's technically not a real force. If you're in a rotating frame, you experience it, and it shapes how you move and how objects behave. This is true on a cosmic scale too. Everything in the universe is rotating relative to something else, which means we're all living in rotating reference frames. Earth rotates. The solar system orbits the galaxy. The galaxy moves through space. There's no absolute frame of reference, no perfectly still vantage point from which to observe everything else. Every measurement we make, every observation we record, is from a rotating perspective. and that rotation influences what we see. When astronomers measure the rotation of distant galaxies, they're measuring Doppler shifts, changes in the frequency of light caused by motion. One side of a spinning galaxy is moving toward us, so its light is blue shifted. The other side is moving away, so its light is red shifted. By measuring these shifts, astronomers can determine how fast the galaxy is rotating and how its mass is distributed. And what they've found is puzzling. Galaxies rotate faster than they should based on the visible matter they contain. This is the dark matter problem again, approached from a different angle. The spin of galaxies reveals that there's more mass present than we can see, and that mass is arranged in a halo around the visible galaxy, holding everything together and allowing the outer regions to rotate faster than they otherwise could. We still don't know what dark matter is. It doesn't interact with light, doesn't emit radiation, doesn't seem to interact with normal matter except through gravity. But we know it's there because of spin, because rotation tells us the mass distribution, and the mass distribution doesn't match what we observe. Some physicists have proposed alternative theories. Perhaps gravity works differently on galactic scales. Perhaps our understanding of inertia needs revision. But so far, the dark matter explanation fits the data better than any alternative. The universe, it seems, is full of invisible matter that only reveals itself through its gravitational effects on spinning systems. And then there are spiral galaxies, those beautiful pinwheel structures like our own Milky Way. The spiral arms aren't permanent features rotating with the galaxy. If they were, the galaxy would wind up tighter and tighter over time, the arms wrapping around the center like a spring. Instead, spiral arms are density waves, regions where stars and gas are temporarily more concentrated, creating a bright arm that rotates through the galaxy at a different speed than the stars themselves. Think of it like a traffic jam on a highway. The cars move through the jam, but the jam itself might not move or might move at a different speed. Similarly, stars orbit the galactic center, but as they do, they pass through spiral arms, regions where the density is higher and star formation is more active. The arms glow brightly because young, hot stars are forming there, and those stars are so luminous, they outshine everything else. The spiral pattern persists, even though the individual stars contributing to it are constantly changing. This means that our sun has passed through the Milky Way's spiral arms multiple times during its 4.6 billion year journey around the galaxy. Right now, we're located between two major arms in a region called the Orion Spur. In another 100 million years, we might pass through one of the main spiral arms, entering a region of higher density, more stars, more potential hazards from nearby supernovae or passing stellar systems. And all of this, the spiral structure, the density waves, the rotation of the galaxy, exists because of angular momentum imparted during the galaxy's formation billions of years ago. The spin is ancient, encoded into the structure of the galaxy itself, and it will persist for billions of years to come, slowly evolving as the galaxy interacts with neighbors, accretes new material, and continues its endless rotation through space. As you breathe slowly, settle deeper into rest, consider how many spinning systems you're part of. Your molecules are made of spinning particles. Your cells contain rotating molecular machines. Enzymes, proteins, Even the flagella that some bacteria use to swim are literally rotary motors, spinning structures that propel the cell forward. Your planet spins, your star spins, your galaxy spins, and somewhere in that vast nested hierarchy of rotation, there's a thread that connects the quantum spin of an electron to the rotation of a galaxy cluster billions of light years across. Everything spins. Everything is connected by that spin. And as you drift towards sleep, you're participating in that cosmic rotation, part of the universe's endless, beautiful motion through space and time. There's a thought experiment in physics that reveals something profound about spin. Imagine you're an astronaut floating in deep space, far from any planet or star, with no external reference points. You can't see anything but distant stars in every direction. Now imagine you start spinning. How would you know? There's nothing nearby to measure your rotation against, no fixed point to compare yourself to. And yet, you would know. You'd feel the centrifugal force pulling your arms outward. You'd feel dizzy. Your inner ear would detect the rotation. Somehow, even in the emptiness of space with no reference frame, rotation is absolute. You can tell the difference between spinning and not spinning. This troubled physicists for centuries. Ernst Mach in the 1800s proposed that rotation must be defined relative to all the mass in the universe, that you feel centrifugal force not because you're rotating in some absolute sense, but because you're rotating relative to the distant stars and galaxies. This idea, called Mach's principle, suggests that inertia itself, the resistance of objects to changes in motion, arises from their relationship to all other matter in the universe. Einstein was influenced by Mach's ideas when developing general relativity, though the final theory doesn't quite implement Mach's principle in the way Mach envisioned. But the question remains, why is rotation absolute when velocity is relative? You can't tell if you're moving at a constant speed through empty space. There's no experiment you can perform inside a sealed spacecraft that will reveal your velocity, but you can tell if you're rotating. Spin is somehow different, somehow more fundamental than simple motion. And this asymmetry between rotation and translation, between spinning and moving in a straight line, is one of the deep mysteries of physics, connected to the structure of space-time itself. General relativity tells us that massive objects create curvature in space-time, and that curvature is what we experience as gravity. But rotation creates its own kind of distortion. A spinning mass doesn't just curve space-time, it twists it, dragging space-time along with the rotation in a phenomenon we mentioned before called frame dragging. Near a spinning black hole, this effect is so strong that space-time itself is forced to rotate. But the effect exists everywhere. Rotation exists, even here on Earth, even around you as you spin with the planet. In principle, if you could measure with sufficient precision, you could detect the frame dragging caused by your own body's rotation if you were to spin rapidly in empty space. Your mass, however small, would twist space-time around you, creating a minute gravitational effect that propagates outward. You're not just moving through space-time, you're shaping it with your motion. Every spinning thing, from electrons to galaxies, creates these ripples in the fabric of reality, and those ripples can travel. When two black holes orbit each other, spiraling closer and closer until they merge, their rotation creates gravitational waves, literally waves in space-time that propagate outward at the speed of light. In 2015, The LIGO detectors in Louisiana and Washington state detected gravitational waves for the first time, ripples from the merger of two black holes 1.3 billion light-years away. The signal lasted only a fraction of a second, a characteristic chirp as the black holes spun around each other faster and faster before merging. And in that signal, scientists could read the spin of each black hole, the speed of their orbit, the mass of the final merged object. Gravitational waves carry information about rotation across the cosmos. Every binary system, two stars orbiting each other, two neutron stars spiraling inward, two black holes dancing, creates gravitational waves, and those waves encode the angular momentum of the system. The universe is filled with these ripples, a constant background of gravitational radiation from rotating systems everywhere, though most are far too weak for us to detect. But we can detect the strong ones, and each detection teaches us something new about how rotation works at the extremes. We've now observed dozens of black hole mergers, and everyone reveals black holes spinning at different rates with different orientations. Some black holes spin slowly, others spin at nearly the maximum possible rate, rotating so fast they're on the edge of tearing space-time apart. And the variety tells us that black holes form in many different ways, under many different conditions, each one preserving the angular momentum of its formation in its eternal spin. Let's return to something smaller, but no less significant. Inside every living cell, there are molecular machines that quite literally spin. ATP synthase, the enzyme that produces ATP, the energy currency of all life, is a rotary motor. It has a spinning component that turns as protons flow through it, and that rotation drives the chemical reaction that creates ATP. This isn't a metaphorical spinning. It's actual physical rotation at the molecular level. A tiny turbine driven by the flow of protons across a membrane. Every cell in your body contains thousands of these molecular motors, spinning constantly, producing the energy you need to think, move, breathe, live. Your consciousness, your ability to read these words, your every thought and feeling, all of it is powered by spinning molecular machines smaller than a millionth of a millimeter. The fact that life discovered rotation, that evolution created spinning mechanisms at the molecular level, suggests that rotation is one of the most efficient ways to convert energy from one form to another. A principle that holds from cellular machinery all the way up to hydroelectric dams with their spinning turbines. And bacteria took this even further. Some bacteria have flagella, whip-like tails they use for propulsion, and those flagella are driven by rotary motors embedded in the bacterial cell wall. The motor spins at up to 100,000 rotations per minute, powered by protons flowing across the membrane, and the flagellum rotates like a propeller, pushing the bacterium through liquid. This is the only true rotating structure in biology, a wheel and axle system that spins continuously, not just back and forth. Evolution invented the wheel, but only at the microscopic level, and it uses it to move bacteria through their world. These bacterial motors can spin in either direction. The bacterium can reverse its motor instantly, changing from forward motion to tumbling, which allows it to navigate toward food or away from danger. The switch happens in milliseconds, controlled by chemical signals inside the cell. It's a level of precision and control that engineers can only aspire to replicate in synthetic systems. Consider that for a moment. While humans were still millions of years away from inventing the wheel, Bacteria had already been using rotating motors for billions of years. The wheel isn't a human invention, it's a bacterial one. We just scaled it up and made it visible. And speaking of scaling up, there's a curious fact about how rotation behaves at different sizes. Small things can spin much faster, relative to their size, than large things. A bacterium's flagellum can rotate 100,000 times per minute. A hummingbird's wings can beat 80 times per second. But an elephant can't move its legs anywhere near that fast. As objects get larger, the stresses from rotation increase, and materials have limits to how much stress they can withstand. This is why there's no such thing as a whale-sized hummingbird. The wings would have to be enormous, and enormous wings can't beat fast enough to keep the animal aloft. There's a relationship between size and the speed of rotation that sets limits on what forms life can take, and this same principle applies to celestial objects. Asteroids can spin very fast. Some complete a rotation in just a few minutes, but planets can't. If Earth rotated much faster than it does, the centrifugal force at the equator would overcome gravity, and material would start flying off into space. There's a maximum rotation rate for every object, determined by its size, mass, and material strength. And the universe is full of objects spinning at or near their limits. Pulsars, as we've discussed, spin at hundreds of rotations per second, right at the edge of what a neutron star can sustain. Any faster, and they'd break apart. They're the fastest spinning objects we know of, and they exist at the boundary of what physics allows. But there's a more personal scale to rotation that's worth exploring. When you were in your mother's womb, before you were born, you were already spinning. Not your whole body, but the cells that would become your brain. During neural development, neurons migrate from where they're born to where they need to be, and they do this by rotating as they move. The growth cone at the tip of a developing neuron spins as it navigates through the developing brain, following chemical signals, finding its destination. Your brain was built by spinning cells, each one rotating as it found its place in the network that would become your mind. And even now, there's rotation happening inside your brain. Neurons don't actually touch each other. They communicate across tiny gaps called synapses by releasing neurotransmitters. Those neurotransmitters are stored in small spherical vesicles, and when a signal arrives, the vesicles rotate and fuse with the cell membrane, releasing their contents into the synapse. Every thought you have, every memory you form, every sensation you experience involves molecular scale rotations inside your neurons. Consciousness itself may emerge from these countless tiny rotations, from the spinning of molecules, the turning of proteins, the movement of ions across membranes. You are, in a very literal sense, made of spinning things. And those spinning things give rise to everything you are. There's something almost poetic about the fact that spin appears at every level of reality. Quantum particles spin, molecules spin, cells contain spinning motors, bodies rotate as they move, planets spin, stars spin, galaxies spin. The universe is a symphony of rotation, each scale harmonizing with the others, all connected by the same fundamental principle. Angular momentum is conserved, and conservation of angular momentum means that spin, once created, persists. It can be transferred, divided, combined, but it can't be destroyed. The spin of the universe today is the same total angular momentum that existed at the moment of the Big Bang. just redistributed across countless objects. Every spinning galaxy, every rotating star, every quantum particle with its intrinsic spin, all of it adds up to a total that has remained constant for 13.8 billion years. This means the universe has a memory. The spin of objects today tells us about their history, about the collisions and interactions that shaped them, about the clouds of gas they formed from billions of years ago. When you measure the rotation of a planet, you're reading its biography written in motion. When you observe a pulsar spinning 700 times per second, you're witnessing the preserved angular momentum of a star that died millions of years ago. Spin is history made visible, and it's also the future. The rotation of black holes might contain the key to understanding quantum gravity, the theory that would unite general relativity and quantum mechanics. The spin of galaxies tells us about dark matter and the large-scale structure of the cosmos. The quantum spin of particles is the foundation of quantum computing, which might revolutionize technology in ways we can barely imagine. Rotation isn't just a feature of the universe. It's a tool we're learning to use, a principle we're harnessing to understand and shape reality. But beyond all the science, beyond all the measurements and calculations, there's something deeply beautiful about the fact that everything spins. There's a unity to it, a connection that runs from the smallest particle to the largest galaxy. You're not separate from that cosmic motion, you're part of it. The atoms in your body contain spinning particles. The cells in your tissues contain spinning molecular motors. You're standing on a spinning planet, orbiting a spinning star, moving through a spinning galaxy. And all of that motion is part of a single, unified cosmic dance that's been ongoing since the beginning of time. As you settle into sleep now, as your thoughts slow and consciousness begins to fade, remember this. You're not really becoming still. You're always spinning, always moving, always participating in the universe's endless rotation. Even in the deepest sleep, even in perfect stillness, you're racing through space at 1,000,000 miles per hour, spinning with the Earth, orbiting with the sun, moving with the galaxy through the cosmic dark. And that motion is ancient beyond comprehension. The spin of the galaxy was old before the sun formed. The spin of the sun was established billions of years before you were born. The quantum spin of the particles in your body has existed since the first moments of the universe. You're not just living in a moment of cosmic time. You're part of a continuous motion that connects the present to the deepest past and the furthest future. There's a comfort in that, if you think about it. Nothing is truly static. Nothing is truly alone. Everything is connected by motion, by rotation, by the endless turning of existence. You're part of something vast and eternal. Something that was here long before you and will continue long after you're gone. And in this moment, as you rest, as you let go of the day and drift toward sleep, you're exactly where you're meant to be, spinning through space, held gently in the arms of gravity, moving with the cosmos in its ancient, beautiful dance. The universe is spinning, has always been spinning, will always be spinning, and you're spinning with it, now and forever, part of the eternal rotation that defines existence itself. Rest easy in that knowledge. Let it carry you gently into dreams, and know that when you wake, you'll still be spinning, still moving, still part of that cosmic motion that connects everything to everything else. Thank you for taking this journey through the spinning universe. If this exploration brought you some peace, some wonder, or some comfort as you drift toward sleep, I'd be grateful if you'd subscribe for more gentle journeys into the profound mysteries of existence. Until next time, rest well, and remember, you're always spinning, always moving, always part of the cosmos. Good night.